which we call the quasi-static limit. So this is a technical term that we use. This means that the final state of the cold bath is also a thermal state according to some temperature. And the limit just means that I'm taking the limit where the final temperature is very, very close to the initial temperature of the cold bath. So G here would go to 0. And in this limit, Carnot efficiency is achieved, and it is achieved uniquely by this. You also will realize that in one cycle of the heat engine, you will have an infinitesimally small amount of work. Okay, so let's try to now slightly relax the conditions on what we want to call work. So what if there is a small failure probability in extracting work? The first thing that you will note is that this causes an entropy increase in the final state of the battery. So you can intuitively think of this as energy not stored only as work, but also there is some non-negligible amount of heat that is present. An example will be the initial state being the same as before, where the final state is with probability 1 minus epsilon, I succeeded, extracted some amount of work, and with probability epsilon, I failed, and the state stays put. Then the change in entropy will be given by the binary entropy of the parameter epsilon. This will motivate us to define something called near perfect work. It means that the ratio between delta S over the amount of work that extracted here is arbitrarily small. So it's very close to perfect, but epsilon is still positive. This will give you a slightly varied version of what you have seen before. And you have the entropy term entering how much work you can extract. And maybe one thing to note is that here I have used a very specific example of the battery states, but also in our paper we proved that more generic battery states can be allowed. So the definition is only for this ratio of delta S versus with such a characterization of work, we still can recover Carnot's result if we assume the macroscopic second law, so only the free energy. You will still get that the maximum efficiency is Carnot. It's achieved independently of the Hamiltonian. It is achieved uniquely at the quasi-static limit.
Just to confirm, so do you mean that if the cold bath and in the thermal state, that's sufficient to get a Carnot efficiency?
The cold bath is yes.
So that's the only condition.
Yeah. Well, no. The condition is that it's in a thermal state, but it's in the limit where the temperature is only slightly increased. So the cold bath doesn't vary very much.
In the resource theory framework for thermodynamics, time is often a tricky subject.
Yes.
So how do you model a quasi-static process? How are you modeling the speed with which your protocol proceeds?
So this is always a point of confusion. When people talk about quasi-static, usually people will think about time scales, infinitely slow process. In the resource theory, you never have time scales coming in because you always assume that you implement a certain unitary. Of course, that will correspond to some kind of interaction Hamiltonian acting for an amount of time. But then this becomes a bit tricky. So quasi-static here just simply means that the final state is not very different from the initial state. It only varies a bit.
And, well, I would expect to apply that definition at each step in a many step process. As in, suppose that I'm dealing with gas in a box and I'm pushing the piston, then the initial state differs just a very tiny amount from the final state. If the final state is the result of pushing in the piston by delta x, and then I reapply that definition to the next delta x and the next delta x. So you apply this definition to each of many unitaries that you're applying?
Yes.
Okay.
Yeah.
Thanks.
So we've seen how our model performs in the limit of the classical thermal regime. The question is what happens when we have generalized second laws in control instead. So this is what we will see next. So generalized second laws, does perfect work? Any guesses on how it should turn out? So if I assume perfect work, no positive amount of work can be extracted from such a setting. And this is, mathematically speaking, this is because of a certain condition on the generalized free energies. It's the F0 term. And this comes from, so it's related to the alpha relative entropy, where the parameter is equal to 0. You can intuitively think that what happens here is because I start out with the thermal states, and thermal states are of full rank. So this full rank problem is precisely what impedes you from having zero probability of failure in the work extraction process. Although it might seem really unreasonable, why should it be the case? You actually have a very nice analogy in data compression for this example. So this is a visualization of what data compression is. It means that you're sending some symbols across the channel, and depending on the redundancy of the data that you have, for example, if your data is all just zeros, then you just need to send one symbol, 0. It means that you can effectively reduce the size of the file that you want to send across the channel. But if you want to do this with zero probability, it cannot be achieved if your data corresponds to the full, the probability distribution of the full rank. And this is exactly what happens here with work.
So your previous conclusion was that you got the combo.
Sorry?
You analyze the perfect work case with classical constraint.
Yes. Yes.
And in that case, you got sort of the standard answer,
Yes.
but now it turns out to be complete.
Yes. Yes.
Now
That's right.
here you have one constraint. You consider for constraint, it was an illusion.
Correct. So, given that perfect work backfired, let's use near perfect work instead. And this is nice in the sense that once you see a positive amount of error probability is allowed, then you can pretty much extract work and you can get very close to Carnot efficiency as well. So you still have recover sum of Carnot statements. It's always an upper bound to the amount of efficiency. It can be achieved. Whenever it's achieved, it happens uniquely in the quasi-static limit. This we prove that, well, for non-quasi-static cases, Carnot efficiency cannot be achieved. And for the quasi-static case, for near-perfect work, what happens is that since G goes to 0, for near-perfect work, what you need is that you choose epsilon as a function of G, such that this ratio will go to 0 in the quasi-static. The thing here, which differs again from our understanding of classical thermodynamics, is that Carnot efficiency is now not always achievable for all cold bath Hamiltonians. So what happens here is that we can particularly derive certain conditions on the cold bath Hamiltonian, such that when these conditions are not satisfied, the efficiency is strictly bounded away from Carnot. We can do that for under the assumption that the Hamiltonian of the cold bath will consist of multiple qubits. And let's first denote the smallest energy gap as E-min here. And then we define this function omega. This is a function of E-min and the inverse temperatures of both gas coming in here. And what we show is that if this quantity is less or equal than 1, then Carnot efficiency is attainable. You still have it uniquely in the quasi-static minute. One thing which is nice about this is that it can be achievable even when the cold bath consists of 1 qubit. So finite bath, at least on one of the baths, you still achieve the Carnot efficiency. Whereas if you have omega greater than 1, then the efficiency maximum version will be strictly upper bounded away from Carnot value. And the one for quasi-static engine is derived as having this particular mode. Why? Why, oh why? So, at the first glance, we see that these results are these findings are a result of the fact that you simply have more laws in the small quantum regime. And these laws will form additional restrictions on how much work you can achieve. But because this is so counterintuitive, you always have people who need to check this carefully. Check that everything is still safe. So I agree with that approach. So let's ask ourselves a few questions. So first, have we checked that Carnot's result is recovered if only the standard second law is considered? This I have showed you. So the model still recovers Carnot's results when the second law is there. Now, it's also the question of, which is kind of similar here, have we considered the most general heat engine setting possible? Maybe it would be helpful to have a look back at the assumptions that we stated at the beginning. So under these assumptions, if you believe that they are generic enough, then this should convince you that it's not a problem of the model. The third challenge that was always frequently posed to me is, have we quantified work correctly? Is near perfect work just an overly stringent requirement on how much work that I extract? And this is a very good question and very relevant to the field as well, because that was the problem, how to quantify work. So to make a complement from the analysis that we have previously, what we do is to consider now all the other different kinds of characterization. We look at epsilon equals to 0. We look at epsilon positive, but in this certain limit where the ratio of delta S over W goes to 0. Now, let's just look at the rest, imperfect work. So here we will focus on analyzing the quasi-static limit, again, because we have proven that the quasi-static limit will achieve the Carnot efficiency if it's achievable to begin with. So case 1, this limit exists, goes to some positive constant p. The results are that the macroscopic second law tells you that Carnot efficiency can be surpassed. But the macroscopic second law will tell you that the Carnot efficiency remains an upper bound. On the other case, you have examples of this ratio going to infinity. Now this does not mean that delta S goes to infinity. It just simply means that both terms are infinitesimal, and this term converges to zeros lower than W. And here, what you can see is that if you apply the microscopic second law, which is already more stringent than the macroscopic one, you can already find examples of surpassing the Carnot efficiency. So that statement is actually, this thing is one whole paper by itself. And the reason for doing that was really to justify that perfect work and near perfect work is supposed to be the way to go. Otherwise, you will somehow surpass Carnot efficiency. Unless you are willing to accept that you will surpass Carnot without the use of additional resources such as exhaustion of entanglement, coherence, etc. So maybe that will convince you to pick the last term. Did I? Anyway, so this is the conclusion. So in our analysis of heat engines, we wanted to make something which is generic enough so that the community can use. This motivates us to make a way to quantify what is good quality work in a microscopic regime. And then we find that in different regimes, you have different outcomes. Some you can achieve Carnot, some because of the second laws, you don't quite achieve Carnot. Carnot when certain conditions are not satisfied. And for some definitions of work, even if you come up with a protocol that achieves Carnot, you must be careful to check that that work is actually good quality work instead of being tainted with heat and so on. So this was a very long project for me, but it's still ongoing because there are a lot of questions that one can still tie up here. For example, one thing that I would like to understand more is that because now we only derive this condition for achievability of Carnot for cubic Hamiltonians. And the question is, what can we do when the Hamiltonian is more generic? And I'm also more interested in looking at realistic thermodynamical protocols, where maybe you are not achieving Carnot efficiency, but it's more realistic in terms of faster to implement or extract more finite amount of work per round, etc. So this can go on, but I think I will stop here. And thanks for your time.
Any questions?
You mentioned that there are many, many examples of particular realizations of quantum thermal machines. What to you makes one of these papers interesting and worth looking into? There are so many that we can't possibly keep track of all of them. I get the impression that some of the papers are just, here is yet another system with which we can realize a heat engine. I can't tell what the motivation is. Is there a good reason for considering this sort of machine and this sort of platform? Does it do anything particularly new and useful? What to you makes one of these papers interesting and worth looking into?
Well, there are a few aspects. They can be quite exclusive in some points. For example, I mentioned that one of my favorite examples is the one from the automechanical machine. I like that because it was very physical. I know what was there, as opposed to the case where you build one out of Q-chips and you have trouble visualizing what is exactly there. I like such examples, but I also find that there's usually a spectrum, because I always like to look at heat engines which do give a detailed justification of what is work and what is not. And physical, concrete, more physics realizations of the examples of heat engines usually don't care so much about these justifications. So, I don't know. It's not super clear.
So in your optimal protocols which achieve Carnot efficiency or the best you possibly can, what is the state of the hot bath?
What is the state of the hot bath?
That's the free one. That's the free one with respect to the resource field.
Yeah.
So is there a particular form you take for it, or?
No. So it would be very nice to prove that all of the possible interactions can be realized by a subset of particular baths. But this is a problem in resource theory by itself already. And in particular, what is the dimension, what is the structure, etc. And there doesn't seem to be an answer yet, a definitive one.
Maybe I missed something, but there seems like there is an asymmetry between your hot and your cold bath. Like you're getting these Carnot efficiency bounds depending on the structure of your cold bath.
Yeah.
While the heat bath is just free to be, well, the hot bath, sorry, is free to be whatever it likes.
Yeah.
So it's like the two baths aren't on the same footing.
Yeah, it's more like once you specify a bath, me being the cold bath, does there exist a hot bath that will give you the transition? Well, if you are interested in fundamental limits, meaning that allowing the full power of you to choose and generate bath states, then this is very valid, of course. If you are interested in specific implementations of a certain process, then maybe this is not a very good statement. But